As my slide suggests, I will focus on the requirement of cooling water treatment in any steel plant. As the schematic suggests, raw material is converted to molten iron, then it goes to molten steel by basic oxygen furnace, and then it goes for continuous casting, and then for various other byproducts. In the process, there are so many cooling water systems which come into play. I'll touch upon only the final stage where water is to be treated, and it plays a very important role. That's the continuous casting plant. In a continuous casting plant, molten steel is casted in the caster. It's a very high heat flux area. When molten steel enters into the mold, and then after a slow cooling, it converts into slabs. So the cooling is done by water, and that water at every stage, when it comes from ladle to mold, and then in the strands for final cooling. These are the various cooling water circuits in any continuous casting plant. There are 4 types basically: mold cooling system, ladle cooling system, machine cooling system, and there is a direct spray cooling system. All these cooling systems have different kinds of problems. They have been categorized into two categories. First is closed cooling system, and second is open evaporating cooling system. And any cooling system, water treatment is selected based on various parameters. These are some of the important parameters, and in that, system characteristics, water quality, plant design, metallurgy of the system, and operating characteristics, what kind of microbiological contaminations, any kind of contingency measures, environmental regulations, flexibility in operational, whether that is considerable or not, and various experiences of the past. All these factors play a major role to work out a tailor-made program which suits best to achieve the desired result. Mold cooling system, where water is very important, and what kind of, I will touch upon in very brief, the very important facts. Like mold cooling systems have specific characteristics. It has a very high heat flux area, and any amount of thin deposit can impede the heat transfer, thereby affecting the final production. So water must provide in a very uniform way at a very particular rated velocity, and quality of water must be very good. So in order to have a proper heat transfer and cooling water in achieve the cooling, the desired result out of this cooling water system, a special treatment is utilized. This is a schematic of any mold cooling system where at a different stage water sprays are done. There is another system which is also utilizing the closed cooling water. This is called machine cooling water system. This is an area where various type of machines, which include pinch roll, heat exchanger equipment, various type of hydraulic fluid coolers, water jacketed pumps, valves, this needs to be cooled, and a very high degree of water is required. As we all know, if water left untreated, it will have three major effects. It will corrode the system, corrode the equipment. So corrosion is a big problem in any cooling water system. Second is deposition, and third is microbiological contamination or fouling. So as we have seen in the previous slides, in mold cooling circuit and machine cooling circuit, a high purity of water is used, which is often softened or DM water. So by using that kind of water, we are able to avoid deposit problems which might be due to the dissolved solids present in the water. So we are finally left with the corrosion problem. And to treat the water with respect to corrosion, these are the basic chemicals which are used. Prominent among them is nitrite, molybdenate, blend of nitrite and molybdenate, azole, silicate, hydrazine, and another oxygen scavenger pH. I'll touch upon the brick property of various type of chemicals. Nitrite is very widely used and it is basically an anodic corrosion inhibitor. It forms a passive magnetite film on the metal surface and thereby protects it from corrosion. But there is a major problem with nitrite. It can be rendered ineffective if it is converted into the nitrate by microbiological activity. So one has to control microbiological activity also. The next compound is molybdenate. Molybdenate is an anodic inhibitor. It's a very strong next to chromate in its category for having corrosion emission property. It reacts with iron to form ferrous-ferric molybdenum complex. That's a very strong passive film, and this does not get affected, unlike nitrite, by microbiological activity. This is also compatible with glycol, which are used generally in chiller systems of smaller circuits. But molybdenate is very costly and nitrite is very cheap. So in order to have the best effect, best synergistic effect cost-wise, the blend of nitrite and molybdenate can be used. And this provides the strength of both nitrite and molybdenate. This compensates the limitations of each, and finally their outcome is it's very cost-effective. Azole is another compound which is primarily used for copper corrosion control. Copper is the major metallurgy in any continuous casting system. Mold is only copper. So azole is a must for any mold cooling system. It provides anodic corrosion inhibition on the copper metallurgy. This is used to provide corrosion protection for copper and its alloys also. It prevents general as well as localized corrosion. And nitrogen atoms forms coordinate bonds with copper oxide molecules to form a corrosion emission film. There is one more chemical which is compound silicate, which is used, can be used, but this is not prominently used in India. This is also a very good corrosion inhibitor, anodic corrosion inhibitor. This can protect ferrous pipes, also lead, copper alloys and aluminium. This hydrolyzes to form Rayleigh charged colloidal particles. So because of various limitations, silicates are not used. And finally, hydrazine and pH. This is basically an oxygen scavenger, and it should be used in a pressurized and high temperature systems. And there is a negative attached to this, that this might get reduced. This reduces the oxygen content in the water. As I said, this is an oxygen scavenger. Thereby, finally, arresting the potential, reducing the risk of corrosion. And this in closed system, as the chances of microbiological activity is very high, so we also uses non-oxidizing biocides. These biocides control all the microbiological growth, be it in bacteria or fungi. and this also stops the
So if